content, recap, implicit and explicit scheme, advection equation, and different schemes. So basically what we have learned till now that discretization is the crux of CFD. What is discretization? Discretization is replacing the derivatives with some equivalent term. In finite difference, we replace every derivative, whether it is time derivative, whether it is space derivative, with some equivalent algebraic formula. So if we have partial differential equations, del u by del t equals to alpha del to u by del x2, which is unsteady one-dimensional heat equation. So if we discretize this time derivative, forward finite difference, and there is a space second order space derivative with a central finite differencing strategy. So this will be called an FTCS strategy or FTCS scheme. So we will get uin plus 1 minus uin divided by del t. So where I is the x direction index and n is the time index, and n plus 1 is the future time level which we want to know, and n is the current time level at which we know the properties of u or the information of u. Del t is the time step, means the difference between n time level and n plus 1 time level. Similarly, the second order space derivatives finite difference equivalent can be written by this, and the truncation order of this, if you expand it, you will get that the truncated series, in the truncated series, the neglected terms have del t and del x2 order. So basically there are two types or two basically categorization of schemes when we talk about finite differencing: explicit method of finite differencing and implicit method of finite differencing. So take a look at the previous equations. We have discretized del u by del t as forward in time and del 2u by del x2 as central spacing. By central spacing means we are calculating the second order derivative at I, and we are utilizing the same number of points from the right side and from the left side. In explicit method, all the known terms are expressed, all the unknown terms are expressed in as a function of known terms. Here uin plus 1 is unknown and other quantities are known at time level n. N is the current time level, and I minus 1 is the node at the left of the I, and I plus 1 is the node at the right of the I. So if we put n equal to 0, where n equal to 0 means we are at time t equal to 0. So the value of u at any I node at time n equal to 0 is known. Similarly, the value of u at node I plus 1 at n equal to 0 means time t equal to 0 is known. So we can calculate the value of u at the future time level, that is n plus 1. Or if we have put n equal to 0, so value of ui at 1 means first time level you can calculate. So in a similar manner, we will proceed. We will put n equal to 1, and because in the previous iteration we have calculated the value of u at every node at n equal to 1. So we know all these terms for n equal to 1. So if we put n equal to 1, it becomes ui time level 2. So in a similar manner, we can calculate the value of ui at different time level. So in this method of solving schemes are called marching procedure. So we march in one direction and calculate the quantities from the known variables. Implicit method. What happens in implicit method, that del 2u by del x2 is approximated using the future time level and current time level. So we can write that ui plus 1n as an average of u value of u at I plus 1 at the current level plus future level. Similarly, we have done with value of u at I node. And in this algorithm, you can see that only value of u at n time level is known. N is the current time level. And there are many unknowns like ui at the future time level, ui plus 1 at the future time level, and ui minus 1 at the future time level. So to solve this equation, we write this algorithm at each and every node of the domain, and thus resulting a set of algebraic equations. So we write at I equal to 0, at I equal to 1, at I equal to 2, at I equal to n, these equations. So this results in an n number of equations. And all of these equations are solved simultaneously to get the value of u at future time level. Explicit method and implicit method both have their advantage and disadvantage. Explicit method is straightforward, very easy to set up, very easy to code, but there is a constraint on mesh size which will be discussed when we come to error and stability analysis. Explicit method consume less computer time because in comparison to an implicit method, we will talk about how it consumes less computer time. Implicit method. Implicit method are complicated to set up because we solve a large number of equations simultaneously. So we have to solve a matrix. So it may require a large computer time. However, there is no constraint on the time level, on the time step. So del t can be chosen 0.1, del t can be chosen 0.5. But in explicit method, there is a constraint which is governed by CFL number, that is stability criteria. We will talk more about CFL number and stability criteria in the next lecture. So suppose we have a 1D linear convection equation which is called advection del u by del t plus c del u by del x equals to 0, where u is some property and c is the speed at which this property is convected or advected, right? So we can discretize this using different schemes. Using We will discretize del u by del t by forward finite difference, and we can discretize del u by del x by backward difference or central difference or forward difference. So let us have a look. So if we discretize time derivative forward in time and space derivative in backward in time, then this will be called FTCS. The explicit version of it is ui n plus 1 minus ui n divided by del t, and c ui minus 1. All of this is calculated at time level n, which is the current time level, right? The implicit version of it will become del u by del t will be forward in time, but when we calculate space discretization del u by del x, the value of ui will be calculated at future time level. So del u by del x will be ui n plus 1 minus ui minus 1 n plus 1. So you can see that in these equations, this quantity is unknown, this quantity is unknown, and this quantity is unknown. So we will write this equation at each and every node from I equal to 0 to I equal to n minus 1, and thus resulting in a n minus 1 algebraic equation. And we will solve that algebraic equation to get the value of u at future time level at every node I. So similarly, FTBS can be obtained by discretizing the space derivative terms in backward finite difference formulation. So the backward formulations or central formulation, central formulation of space derivative will be this. So we will utilize node I minus 1 and I plus 1 while calculating the derivative del u by del x at I. But in implicit version, you can see that this derivative is calculated at the future time level by using central differencing in space. Now we will talk about some basic definitions which are very crucial in finite differencing. So what do we want from finite differencing? We want to solve a partial differential equation which we are not able to solve by analytical method. So we replace the derivatives with some equivalent. But there are some conditions which this finite differential scheme must obey to arrive at the correct solution. So there are some definitions like consistency. What do you mean by consistency? So if we discretize an equations, we discretize a partial differential equation, and this partial differential equations discretized version will give values at discrete location in a discrete time level. So this discretized version of partial differential equation must approach to the original PDE as the grid size del x and time level time step del t approaches to 0. Stability. So of course there are some errors when we approximate a derivative. So that error may be because of discretization error, because we have to truncate the series to generate formula for finite difference equivalent of derivative. There may be some round off error because of we are unable to represent 1 by 3. So a numerical scheme will have these types of error. So all of these error must not grow, right? Error will be present, but they should not grow with the iteration or with that is with the when we are solving the equations. Convergence. So what do we mean by convergence? The solution of an algebraic equivalent of PDE can be solved, but are we getting the right solution? We can get a solution, but it must be right solution. Means it must approach to the true solutions. To ensure that the concept of convergence is used. So a finite difference scheme is convergent only when the solution of that finite difference equations approaches to the solution of the original PDE when the grid size approaches to 0. So we will talk more on stability, and there will be a whole lecture on stability. So stability basically is a condition on the numerical solution strategy. Whatever finite differencing strategy, backward, central, or forward we employ, that may not guarantee a solution. It will only guarantee a solution when this strategy is stable, means the all errors are bounded when we are solving the equations. So what stability says that for the finite value of time step and mesh size del t and del x, the error has to remain bounded. So if ui at time level n is the computed solution which we have obtained by solving the discretized version of the solution using a computer or manually solving, and ui bar n is a discretized solution, exact discretized solution with zero round off error of the finite difference equations. Then the error will be computed solution minus discretized solutions. So for stability, when the time step tends to infinity, this error must be lower than a value. The magnitude of error must be bounded in a certain region. Now we will talk about Lax theorem. So we want to solve a partial differential equations by approximating it, but we have to ensure that it has converged. So a Lax theorem say that a well-posed initial value problem for a consistent discretization scheme, stability is the necessary and sufficient condition for convergence. It means if a finite difference strategy is consistent and stable, then we can be ensured that the solution obtained is converged. So let us have a look at this diagram. We have a differential equation del u by del t, and we discretized it using some strategy. So an scheme will be consistent if in the limiting case this discretized version approaches to the differential equation original PDE. So we will solve this discretized version. So numerically we will numerically solve this discretized version. So there will be some numerical solution of discretized equations which will have round off errors. So this round off error must be contained to have stability, right? So Lack's theorem says that if we have ensured stability and consistent, then we have ensured convergence. These are the references. These are the questions which you have to address. Thank you.